Hello everyone, this is lecture Jawad Syed and we will conduct the first lecture in our sort of online distance learning system. So we will continue after steam turbines, covering steam turbines, and we will start with the topic of gas turbines. ठीक है ना? I will sort of conduct this lecture both in English and Urdu. So based on your feedback, we will figure out how to move forward through this. Uh, you guys have the advantage of actually revisiting this lecture and pausing and rewinding wherever you want. So I can I will not be able to obviously answer your questions as the lecture is conveyed to you, but we will have question answer sessions and discussion sessions based on how the lectures go forward, because we will unfortunately have to do this for a long time. So let's get on with gas turbines. Gas turbines जो हैं, they are the second most sort of common mechanism of producing power after steam power plants, and they are most commonly used in, first off, jet propulsion. Like all of the aircraft you see here, they are turbojets, prop jets, etc., etc. But a lot of them employ some sort of a gas turbine. अब जो aircraft है, that's primary purpose is to move forward, right? It has to just create thrust and it has to just move in the air. So you don't want a lot of power generation from it. It's not like we are driving a small town or a small factory from it. We just want enough power to drive the compressor and a small generator to power the auxiliary equipment, जो भी electrical उसमें devices है, etc., etc. Obviously, there are batteries involved. It's not like if the turbine starts to slow down, the electricity produced, like the electrical devices will get less power, and when it ramps up, we get overvolted. But it's just producing enough power to for the compressor and the auxiliary equipment. The rest of it is thrusted out of the exhaust and produces the produces thrust for the aircraft as a reaction force, right? Second objective is, which is most interesting to us, is the power generation side. Power generation के लिए, like a lot of the natural gas power plants you commonly hear about are gas turbines. So they are big power plants. They are installed in the ground in factories, and they produce power by the same sort of principle, but their focus is more towards generating electricity or generating mechanical power from the turbine shaft. Because mechanical power sometimes is also applicable towards marine applications, and we can see uh, large ships also employing some gas turbines, जहाँ पे we don't want to use IC engines because the application is so large, and if we can, we want to have a very efficient power generation system, because traditionally आप लोगों ने जैसे पढ़ा है, the vehicle engines, auto cycle, diesel cycle, they are not that efficient compared to a gas turbine cycle. ये हम इसको further भी देखेंगे. What are the gas turbine cycles, ठीक है? But right now, commonly we have a direct open gas turbine. बहुत simple idea है. We just take a gas turbine example and imagine these are the compressor blades and the combustion blades and the turbine blades. We just add fresh air. We add fuel here. We burn it here, and we produce power there and just exhaust the gases out. This is one of the most common examples, which is commonly seen in the jet aircraft. You draw fresh air, you burn it, you produce power from it, and you just exhaust the rest of it. Uh, but again, we have a second example, which is indirect open. Indirect open में क्या है? For example, आपके पास एक coal reactor है, coal furnace है. अब आपने देखा है, we went to, as you might remember, we went to the Askri cement factory, and you might also remember the coal residue and उसके exhaust के ऊपर you can see very commonly wherever there's a coal furnace, it has a lot of sort of impurities, and those impurities tend to stick to the surfaces. अब आप ये नहीं चाहते कि you run the turbine and you have the turbine blocked after a certain amount of time because coals has stuck to it. So coal residue is stuck to it. So what you do is आप fresh air तो draw करते हैं, but you have the fuel burn in a separate compartment. ठीक है, और वो जो compartment है that just takes heat and that gives the heat to this fresh air, and this fresh air sort of gets hot and produces power in the turbine. Okay? So the principle is same. Like instead of just fuel mixing in the air and then this is the fuel air mixture, you just have the fuel air mixture separate and this sort of goes either away or back to the reactor. This is also common for न्यूक्लियर रिएक्टर्स और सम अदर फॉर्म ऑफ रिएक्टर्स जहाँ पे फॉर एग्जांपल अगर आपके पास बॉयलर है, ठीक है ना, आपने स्टीम पावर प्रोड्यूस करनी है एंड यू स्टिल गेट दिस एग्जॉस्ट एयर एट लाइक 700 डिग्री सेल्सियस और 1000 डिग्री सेल्सियस. So you want this hot air to be utilized as well. So you just take this and add heat to some fresh air and produce power from it. उसके बाद हमारे पास एक जो थर्ड कैटेगरी आ जाती है, दैट इज अ क्लोज्ड टाइप गैस टर्बाइन. ठीक है, क्लोज टाइप गैस टर्बाइन सबसे कॉमनली आप इस तरह देख सकते हैं कि द व्हीकल इंजन साइकिल्स, ऑल्दो दे आर ओपन साइकिल्स, आप यहाँ से फ्रेश एयर लेते हैं, fresh air and fuel लेते हैं, you compress it, you burn it, you take power out of it and you just exhaust them. But to complete a cycle, to study that IC engine, you sort of connect this exhaust and this intake and you sort of assume that there is a heat exchanger. Similarly, a lot of the gas turbines in practical terms are open gas turbines, but to study them in a cycle आप उसमें एक heat exchanger वाला element add कर देते हैं. So there's one example. Second example is in some cases जब आपके पास ये specially nuclear reactor है, so nuclear reactor ने अगर heat exchange करनी है, that needs a lot of very uh, like sort of filtered and purified air, because eventually you don't want to sort of get anything clogged here or anything damaging the turbines or the compressors. So आप क्या करते हैं कि you need to have some advanced filtration mechanisms. अब to waste that filtered air would be wasteful. Like that would involve like all the fresh air has to get. Oops, sorry. Okay, we can sort of carry on this example here as well. Uh, Imagine the reactor here, and every time you need to draw in air, you need to filter it. So that adds cost. So what you can do is you can just simply take the excess heat uh, from this air and just cycle it back and back into the compressor. So that is one application of a um, closed gas turbine cycle. जब आप closed direct heat gas turbine cycle की बात करते हैं, so one of the very common cycles is called a Brayton cycle. Brayton cycle आपने देखा है कि you might remember from thermodynamics that you have some ideal gas cycles, like you have when you write ideal air cycles. I'm trying to get my pen to work, so hopefully the writing will improve further on. But so right now I hope you can just follow my voice and sort of gain some knowledge through the writing. So you have Otto cycle and diesel cycle, which is commonly employed in engines, and then you have Brayton cycle, which is employed in gas turbines. So why Brayton cycle? Brayton cycle allows us to remain very sort of efficient, and it sort of although it takes more area and it involves a continuous operation rather than a reciprocating cycle, which is the IC engine cycle. So you can see that Brayton cycle involves a lot of sort of processes which allow us to have the maximum area available between a specific volume and a specific pressure range and convert that area into work output. So the most ideal sort of work input and output process we have discussed is the isentropic process. And we have discussed that because of the limitation of a reactor and the heat exchanger, we can only have constant pressure, heat input and heat output processes. So Brayton cycle just employs all four of these. So the compression process is isentropic, the expansion process is isentropic as well. We don't need to worry about heat loss here and here. And the heat addition and heat removal process are constant pressure. So this constitutes our Brayton cycle. Then in further weeks, we will study about the different sort of different variations to it, different actual like assumptions that we have taken and how to sort of solve these cycles while reducing those assumptions one by one. But hopefully we will carry on and we will sort of learn uh, gradually how to better understand the Brayton cycle. Brayton cycle जिस तरह भी जहाँ पे भी हम when we are talking about a thermodynamic cycle and a power plant, we are interested in efficiency. Efficiency क्यों? Because we want to have the most work output with the least amount of heat in supplied to the system. Um, in steam power plants, generally the turbine is a very separate unit and that unit sort of produces electricity which is consumed in the compressor. In a gas turbine हमें एक sort of advantage ये होता है कि the turbine and the compressor are both mounted on the same shaft. So as the turbine produces work output, some of that power is consumed in this compressor, and so all the power we get out from this is network. So this is one of the sort of, you can say, advantage, but all the power you receive at the end of this turbine is the network output. One of the very important figures here is called the pressure ratio, which is basically the ratio, like the pressure ratio between the high pressure, the pressure where heat is added, and the low pressure where heat is removed. So the compressor takes adds like the amount of pressure from point 1 to point 2, and the turbine sort of expands the air from pressure 3 P3 to P4. Um, you can see जिससे हम लोगों ने steam power plant को solve किया था, we had Q minus W is equal to delta H. So because this is isentropic process, Q becomes 0, and we have compressive work is equal to minus W out is equal to delta H. So since we have already written compressive here, we can just write plus, and we can just say W compressor is equal to delta H. Similarly, when we go from T2 to T3, since we are only adding heat to the process and we are not extracting any work from it, so this becomes Q minus 0 is equal to delta H. So similarly, 3 to 4, no Q, and you can see here this is minus delta H. So you just write minus here and add this with the plus sign. Similarly, in the last one, again heat rejection, Q is equal to delta H, but this Q comes out to be negative. When you write this Q out, then you can say Q out is equal to minus delta H. This is minus delta H because 1 is after 4. जब आप ये सारे कर लेते हैं, then you have W net which comes out to be W out minus W in divided by Q in. So this equation is also represented by 1 minus Q out by Q in. ठीक है? So Q out by Q in. And अब यहाँ पे जो ये next step है, that assumes this CP is constant. Realistically हमें पता है कि this is not the case where CP, this temperature can vary from, like this can be above 300 to 700 Kelvin, and you know that CP changes a lot between this temperature. But you will see in further calculations why we can sort of take this assumption and how does this assumption help us. But remember this कि ये जो है, this adds inaccuracy to our calculation. So wow, this is so bad. Um, Okay, so like if you have the direct enthalpy figures, that's the best. And if not, you can just take the instantaneous CP value. And even if you don't have that, you can just take then the temperature ratios and solve this. But this is the least uh, accurate. Then this is more, and this is the most accurate figure. Now, because some of our processes are isentropic, we can take some of the isentropic equations, right? T2 by T1 is equal to P2 by P1, K minus 1 over K. Then we have the PV raised to power K is equal to constant, etc., etc. And we have defined earlier that we have a certain pressure ratio which is P2 by P1. You can see that since these pressures are the same, P2 and P3 and P1 and P4, so P2 by P1 is also equal to P3 by P4. And finally, we can take that old equation where we replace the CP values, assume CP was constant, and just add T2 by T1 is equal to pressure ratio K minus 1 by K. And this that whole big equation changes to 1 minus RP K minus 1 by K. Okay, so now you can see, like as you increase the pressure value, this figure goes down and this efficiency approaches the value of 1. You can see it here as well. So जैसे अगर आप 5 पे एग्जांपल लें, so the efficiency value is this, and अगर आप 20 पे value लें, this efficiency is this. This figure is not exactly accurate. Right now we have gas turbines which work at pressure ratios of around 50 to 55. So this is a bit out of date, and pressure ratios for modern gas turbines are a lot wider. But you'll see how increasing the pressure ratio beyond like a certain point is also not helpful for us in some scenarios. Okay, so I've discussed that some of the work from this turbine is used back in the compressor, and that is one of the main sort of drives for a jet engine gas turbine, right? So this is called a back work ratio, where that means how much of the turbine work is consumed back in the compressor, and obviously we are just interested in the absolute values since compressor work is by default negative and turbine work is positive. We are not interested in the positive or negative side, we are just interested in the ratio. This ratio has to be lower than 1, because if this ratio is greater than 1, then the turbine will not sustain its operation, right? If the turbine is not producing enough power, then the system will eventually stop. So this ratio has to be lower than 1. You can see that when we produce power from the turbine, some of the power is consumed back in the compressor and the rest is obtained at the end of this shaft. So some of the limitations do we have in designing a gas turbine is, first of all, it's the temperature. Why are we restricted to about 1700 Kelvin? The very obvious answer is material constraints. Like, we can't design turbines, we can't construct turbines out of like, what do we say, tungsten or something. We need to create turbines with have a specific power to weight ratio and everything, and they need to have a certain rigidity and other constraints. So that puts a limit to our temperature to about 1700 Kelvin. After that temperature, generally you start to see damage happening in the turbine blades, happening in the combustion chamber, etc. So generally we try and restrict. I've commonly seen um, the temperatures to be restricted around 1300 to 1500 Kelvin. So there's that. When you're restricted by the temperature, then the the sort of condition becomes that how much can you take the work output from like आपने एक बड़ा gas turbine install की, you want most work output from that gas turbine because otherwise you have wasted a lot of money. So एक common question आ सकता है कि sometimes you see um, flame coming out of a jet engine, right? Like अगर आपने कभी planes की videos देखी हो, you see a lot of flame coming out of it, and flame is generally much higher than 1700 Kelvin. So what happens there is it is something called a afterburner. Afterburner क्या करता है? Because when we are running a jet engine, we are taking a lot more air than necessary for combustion of fuel. So वो air क्या होती है? That is also available to combust at the end of this whole process. और जब आप एक turbine से भी निकाल देते हैं उस सारे exhaust mixture को, that still has a lot of fresh air in it and a lot of oxygen in it. So when we need to accelerate our plane very fast, like अगर हम for example एक बहुत sudden lift off करना है, या for example we need to go above the speed of sound, then the turbine cannot produce sufficient amount of thrust. So what we do is we just inject fresh fuel into the exhaust of the turbine and we just burn that. So that does not come in contact with the turbine or the original jet engine or the original jet turbine. It just sort of burns and produces an effect like rocket. जैसे आप rocket से एकदम से suddenly exhaust gases बाहर निकालते हैं, so it pushes the aircraft in an opposite direction and you go much faster than sometimes even the speed of sound. Why do we have very large amount of air? Because it is needed for the complete combustion of fuel, and secondly, it is also used as a coolant. So ये एक बड़ा advantage है, especially in comparison to engines as well, because as you might remember, engines are commonly kept at a very specific air fuel ratio. You generally don't go very lean towards, especially in the spark ignition engines, but in sort of uh, gas turbines, you do keep the ratio, air fuel ratio to be very lean because you also want to keep this you also want to take this air in as a coolant, because जब आप 20-30,000 feet की height पे हैं, you are not taking in any sort of, you're not sort of exchanging heat in a conventional manner. You just want fresh air to come in, cool the systems down to a reasonable limit, and then take that excess heat out of the engine. So, uh, first question you can ask is, when we had the uh, common sort of applications, common pressure ratios of gas turbine, okay, why don't we go above 20, or as I said, like sometimes you go above 55? So what happens, why don't we just design all of the turbines to be at the highest amount of pressure ratios they can? What happens is, as you increase the pressure ratio, the efficiency starts to increase. ये आप देख सकते हैं कि जैसे अगर आपने सिर्फ 2 की pressure ratio रखी है, there is a large amount of heat in and a large amount of heat out, ठीक है ना? But there is a very small amount of W in and a very small amount of W out. The efficiency is very low. But as you go towards pressure ratio of 15, there is a very small amount of heat in and heat out, and supposedly there is a very large amount of work output. But you can see that there is a large amount of work input as well. You have to do a lot of work to compress this gas to the combustion chamber. So what happens is you don't get a lot of net work output. This is commonly used in sort of jet engines, because we don't want a lot of sort of output work at the shaft, but we want the system to have a large amount of efficiency. So it can run, especially the commercial jetliners can run at a very high pressure ratios, commonly up to 50 or 55. But so in power generation, we want a good efficiency, but we also want a large amount of network output. So the ideal condition is somewhere in the middle between this 15 and between this 2, which is given as T max by T minimum divided by, or raised to power 2 K divided by 2 multiplied by K minus 1. This is called the optimum pressure ratio, and this gives you the most amount of network output. How you get this pressure ratio, you can see in the coming slides. So this is the common example of this is the equation of W net is equal to W turbine minus compressor, which is delta H. Delta H is Cp delta T here, and you can write in this equation form like this. So when you have pressure ratio of 1, that means there is no compressor work and no expansion work. So that means this is the minimum amount of network. So now anywhere where this sort of derivative becomes 0, that means this system is reached its maximum. So you write this W net as a function of Cp thing, and when you take the derivative, this derivative comes out to be constant becomes 0. 1 over x derivative is like this. Um, and you get the final sort of ratio to be equal to this. So at this pressure ratio, you get 0 as the derivative of W net. That means that you get the maximum amount of network. Okay. This is I'm sure this is confusing by now, but let me just recap this. So at this pressure ratio, you have this derivative to be 0, which means that this sort of W net can no longer increase by increasing the pressure ratio. So okay, after that this pressure ratio starts to decrease, and that means this pressure ratio results in the maximum amount of network, because minimum amount of network is already known to be 0 when Rp is equal to 1. Okay, so you can see this effect here as well. You can see here the efficiency is not the highest it can be. Like you can see the efficiency rising to about 55% at 20, but the work output has decreased from maybe like 270, 275 to 260 in the cycle. Let me just erase this so you can actually make the connection yourself. But I hope you guys have the slides downloaded with you as well. So hopefully this should not be a problem for you guys. Okay. Uh, this uh, this is a very simple thing. Like we, as our steam power plants, we consider some of the actual processes, which means like there is some certain pressure drop in the combustion chamber. There is certain isentropic inefficiencies in the turbine and in the compressor. There is pressure drop uh, in the heat exchanger as well, and so our actual cycle looks. Let me just use a black pen. Our actual cycle sort of okay. Just bear with me. It's hard to retrace with the mouse. Okay, so our actual cycle looks sort of like this, whereas uh, the ideal would have looked like sorry this. Okay, so you can see that the pressure ratio between the point 0.1 and point 0.2a is much higher than point 0.3 and point 0.4a because we have some pressure drop in the heat addition process, and we will have certain pressure drop in the heat rejection process. So you can say that we okay fine we can reduce the pressure from the turbine here, but then eventually it will go further down, and this compressor always has to do more work than like a bigger pressure ratio than the turbine. Okay. Again, similarly as a turbine, this work output will be lesser than actual. So 4s will be lower than 4a. That means this difference H3 minus H4a is lower than H3 minus H4s. So that means this turbine is lower than 100%. But in the case of compressor, the ideal compressor has the lowest amount of work input. So ideal minus original, sorry, ideal minus initial will always be lower than actual minus initial. Uh, for example, like okay, so this deals with the the efficiency considering we have some mass flow rate as well, because the temperatures and pressure ratios are of course limited, like they are not going to go anywhere, but the mass flow rate determines the overall नेट अमाउंट ऑफ वर्क आउटपुट। इसी तरह ये चीज़ थी जो कि स्टीम पावर प्लांट के लिए भी थी, यही चीज़ है जो कि गैस टरबाइन के लिए भी है कि फॉर एग्जांपल यू सॉल्व दिस साइकिल फॉर 1 kg ऑफ mass just moving every second, but then you have maybe like 50 kg per second or 5 grams per second. So the overall power output in watts or megawatts changes by the mass flow rate of this system. So you can see that the efficiency remains the same because the same amount of mass has to be supplied heat, and the same amount of mass provides you the work output. Okay, so we will stop here. We in the next week we will deal with the improvements in the Brayton cycle. These are fairly simplified because sort of commonly both of the improvements we will deal with intercooling and reheating of Brayton cycle and regeneration of Brayton cycle as well. So they are generally all sort of utilized in a same scenario. So uh, we will deal with the improvements, we will deal with the modifications, but rest assured they are simpler than steam power plant. Like with the I can imagine कि जो closed feed water heaters है, open feed water heaters है, उनकी जो arrangements है, they are a little more complicated than Brayton cycle की जो improvements है, they are much simpler. So okay, I will end this lecture with sort of uh, a task for you guys as well. I will share a basic example of a Brayton cycle, ठीक है? And you guys have to try and solve it, and we will have the discussion on that cycle on Wednesday. So Wednesday in the same time slot as the lecture slot, and I will recommend that you guys sort of require that you guys actually go through this lecture. आपके पास power plant की slide भी होनी चाहिए, PowerPoint की, and you just go through the slides and sort of listen to my narration, and इसमें कुछ obviously I've used the cursor for some annotations as well. So आप इसको use करें, आप इससे थोड़ा सा study करें, and you solve that example, solve that basic cycle example. ताकि when we sort of resume our session, you guys should not have to start from ground zero. Okay? So see you on Wednesday, inshallah, and hopefully we will try and improve this lecture format later on, and we can try and uh, maybe have a live sort of lecture as well. But let's see, let's go uh, with this session, and we try and improve it later on. जी, खुदा हाफिज.